Welcome back for lesson 6.4. We are going to carry on with the central limit theorem for sample proportions. And the what we did in 6.3 was all about quantitative data, and now we're going to work with qualitative data. So this is where you're counting maybe the number of yeses, or you're counting the number of blue-eyed people and taking a proportion. So that means our sample proportion is going to be X is the number of successes out of N, which is the number in your sample. And this is called P hat. This is the estimated proportion of successes. Sometimes I'll write it with P prime, but usually we use it as P hat, is what we call that. Okay. And so we have to normalize this just like we did in 6.3, where we create basically a z-score for the particular scenario of the quantitative data. Now we're going to create a z-score for a particular scenario of a qualitative variable. Okay. And so that z-score is going to be using this P hat. So that's our sample proportion, subtracting our scenario proportion of what we think is true, divided by the square root of P times Q over N, which is this right here. So it's the square root of P hat over 1 minus we're using this. It's the square root of P over P hat minus P over the square root of P. You can use Q, or you can just write it as 1 minus P over N. Okay. So to be able to do this, we have to meet 3 conditions. The first condition is that we have to have a random sample. So this is similar to 6.3. Our condition 2 needs to be independent. So our observations are independent of one another. So this is the same as back in 6.3, where we're going to take 20 times our sample size has to be less than our population. And then condition 3 is our normality condition. And that says that the sample size has to be large enough. And so for proportions, we have to show this. This has to be true. N times P times 1 minus P has to be greater than or equal to N. So let's go take a look at that, what that means. In example 1 here. So in 2014, a Pew Research survey asked 1,821 random 18 to 33-year-old adult Americans if they believed alcohol was more harmful to a person's health over marijuana, and 69% said yes. So this is back in 2014. Verify that the conditions of the central limit theorem for proportions have been met. So the first one is, do we have a random sample? And they did tell us that it was a random sample, so we can check that off. But you need to acknowledge it for the quiz. Number 2 is independent. Now, do we think, so as long as we're using without replacement, or with replacement, we don't have to worry, but we are not doing it without replacement. We can't ask a person their opinion and then ask them again. So that means we have to show that 20 times our sample is less than the population. So that means we're going to do 20 times 1,821 people. That's equal to 36,420. And do we think we have a population bigger than this in America? And we would say yes. So I need to see this multiplication for the quiz. So the third thing is normality. Okay, and now because we're talking about proportions, for normality requirement to be met, we have to prove that this multiplication product is bigger than 10. So that means 1,821 times 0.69 times 1 minus 0.69 or 0.31 is equal to 389 0.51, and so that is bigger than 10. So we have met all three conditions. And now, since we've met all three conditions, we can say that our shape should be approximately normal. Our center can be used at the mean of the p-hats, which should be approximately that 69%. And our spread is going to be the standard deviation or the sigma of the p-hats, which should be the square root of 0.69 times 1 minus 0.69 over 1,821. So this is what you would be using to calculate your new z-score. We're going to get practice with this here in a moment. Okay. So suppose you conduct your own poll of 1,821 random adult Americans between these ages, and you find that 67% believe that alcohol is more harmful to your health than marijuana, which would be unusual with a probability of 0.032. Okay, we figured that out, and we know that having 67% is very small. It's less than a 69, and it doesn't seem small, 2 percentage points, but it is. It's less than 5%, which we said is unusual. So what could be three conclusions that you might draw? Okay, these are three typical conclusions that could be drawn. It could be a fluke, right? It could have just happened that you sampled that many people and they are less likely to believe that alcohol is more harmful than marijuana. Okay. It could also be that maybe we don't have a random sample. So that could also be a possible thing that could have happened. The third thing that could also happen is maybe this proportion of 69% that we believed for all this time to be true, maybe isn't really the true proportion. So maybe our parameter is not 69%. That's a possibility. Okay. So let's look at example 2. Let's go through some here where we're getting some numerical practice. So it says, according to a 2018 Vox poll, 45% of Americans report watching the Super Bowl yearly. Suppose a sample of 120 Americans is randomly selected. Describe the sampling distribution using correct symbols. So because we're going to trust that our three things have been met, it was a random sample. If we took 20 times 120, we would definitely have enough Americans to cover that. And if we took our N 120 times 0.45 times 0.55, that would be bigger than 10. So we can say that our sample is approximately normal. The mean of the p-hats, we can use that 0.45. And the sigma of the p hats is going to be using 0.45 times 1 minus 0.45 over 120. Okay. So we want to find the probability that we get a sample that has less than 43%. Okay, so we have to normalize this first before we can go to Alex. So to normalize that, we're going to find our z-score for this situation. So our p hat goes here, just like we would in a z-score, and we're subtracting what we think is true about the population, 0.45. And then our standard deviation that we're using is this, the square root of 0.45 times 1 minus 0.45 over 120. So once we find the z-score here, by taking 0.43 minus 0.45 divided by what we think is true, we can then put that into Alex. So let's go to Alex and see what that says. Well, just one moment.